Might as well jump. All right, Mr. Berto back again with another pre-calc honors video. A little bit of housekeeping at first. Okay, you guys have today is, I believe you're watching this video on Wednesday. I'm making it on Tuesday. So Tuesday is the day that your curve sketching quiz is due. So send that either via email or Remind. It's a lot easier if you do Remind. A bunch of people still aren't on my Remind. Get on my Remind, people, okay? If you have a problem with it or something, let me know, email me, and you don't have to be on there, but it makes things a whole heck of a lot easier. Tuesday, okay, you'll see that there was a take-home test posted. That is not for the topic we just did, curve sketching, okay? That's for the topic that we did before school was suspended. I know it's a long time ago, but it's also a take-home test. Hopefully it doesn't bother you too much, and that grade's going to count in the third quarter. So that should boost up some people's averages along with that curve sketching quiz as well. Will you have a test on the curve sketching topic? I don't know yet, okay? If you do, it'll be a little bit belated. They're take home, so hopefully that won't be too big of a deal, and it'll force you to look at the material again, which is also good. But we're gonna start a new chapter today, get a little star action going. Start! It's not actually really a new chapter, okay? It's actually a continuation of chapter 3. Chapter 3 was applications of the derivative. We started actually applying the derivative. How can it help us out? And we saw last chapter that it can allow us to actually sketch a function without using the graphing calculator. It tells you where a function is increasing and decreasing and has maxes and mins, concave up, concave down. But how does that relate to real world situations, okay? And that's actually what we're talking about today. Chapter 3 continued. We're going to use that curve sketching ability we learned in the last chapter to apply it to real world situations, to do things known as optimization problems. Optimization problemos, or problems. And old school, those used to be referred to as verbal max-min. Look, we'll be doing simplified situations, basically geometric situations, how does this stuff apply to geometric situations throughout this topic. We won't get into the more intense stuff, but there is intense stuff. I mean, there's a reason everybody who wants to major in business has to take Calc 1. You might be like, I got to take Calc 1. What do you mean? Well, you have to know about optimizing, either maximizing or minimizing, okay? Believe it or not, let's just pick like a business today, pretty lucrative business right now, actually be manufacturing these things, right? Manufacturing graphing calculators, okay? Every school is required that you guys need these. They have to provide them for you. So building these days, you got a pretty good consumer base right there. When you build them, okay, look, it's going to cost money to actually build each calculator. You're going to want to sell it for a certain amount, okay? Maybe you start selling calculators, and I don't know, you build a calculator for, these things retail for what, around $80 or something like that, which means who knows what the cost involved is. Maybe it's $40. That's the law of retail, right? Increased by 50%. Maybe it costs $30. Maybe it costs, $10 to make this thing here. The idea is that, as you're selling your calculators, you're going to make more and more money. People start building calculators, they start selling calculators. They're like, yeah, I'm making money right now. I sold 100 calculators. How about I manufacture, 20 billion calculators and sell those? Well, there's not enough people on the planet to actually purchase those calculators. So at some point, there's going to be a maximum amount of calculators that you're going to want to actually build that's going to generate that maximum profit back. And then after that, you're just going to actually end up losing money. So that's maximizing in a real world situation. You could talk about minimizing as well, like when you create these things, what materials are going to use because it costs money. Some people are like, yo, I love my calculator so much, I'm going to make it out of gold, okay? A gold calculator would look really cool. Put it on like a string, wear it around your neck, Flavor Flav style. I would do something like that myself. The only problem is that that's going to cost way too much money, okay? You're not going to be able to sell those calculators for the amount of money you want to if you actually construct them out of gold. So, that's why maybe use plastic, something like that, which is strong and cheap to minimize cost, okay? So you want to maximize profit like we talked about before, but you want to minimize the amount it actually costs to build each graphing calculator. These are important things in business, okay? We're going to talk about them in this chapter with a geometric setting, okay? We won't really get into the business stuff. We'll talk about it a little bit next year in AP, but it's kind of got out of vogue these years. In AP, doesn't mean you won't see that in college calculus, but really, these are multi-step problems, okay? So there's really going to be a process for these problems. All right, you're going to follow this process if you start to get confused. Some people start to think ahead. They think they can, solve the problem just by looking at it. With easier types of situations, yes, but usually that's not going to be the case. Focus on the process, okay? And really, we know how to find out where a function has a maximum or a minimum. We did that last topic. Maybe the function represents profit. You want to find maximum profit. How many calculators do I need to build to get that maximum profit? You want to maximize that function whose y values represent profits, okay? So this f of x, this fictional f of x we had last chapter, now we're going to start putting a name on it, okay? And in these problems, they're always going to tell you whether they want you to maximize something or minimize something. You got to find out what that something is, okay? So the first thing you want to do is find what to maximize or minimize. Find what to maximize / minimize. And then you need to get a function that represents that thing, okay? If you want to minimize cost, you got to get a function that represents cost. So right here, we want to get an equation for that thing. We'll write it that way. Get an equation for that thing. My kids are screaming and yelling upstairs. Hopefully it's not too distracting. Sometimes I like to say this line in my best American Italian. I say, hey, we're going to get an equation for that thing, all right? And you really got to put the hand gestures in there for it to be true American Italian. After that, you want to get that function, which is probably going to be multivariable, down to one variable. We only know how to deal with calculus in one variable here. So get it down to one variable. Get it down to one variable. And by the way, once it's down to one variable, that's going to enable us to be able to get a domain. So then also get a domain, which will bother a lot of people. You could do these problems without even having the proper domain. Okay, so if getting the domain starts to freak you out, because we do it commonsensically at first, but then we try to make it a little bit more of a concrete math thing. If that bothers you, the domain, don't freak out too much about it. Okay, and then finally, we're going to apply the first derivative test. Once we have that function that we want to maximize or minimize in one variable, then we're going to figure out where it has that maximum, where it has that minimum, or what that maximum value is, what that minimum value is. Okay, so if you look at your dittos, we like to start off this topic talking about some crazy fictional character, Old Man Berto. I'm not on Twitter, but if I ever was, my Twitter handle would be Old Man Berto. And here we got Old Man Berto. I'm having printer issues, so I sympathize with everybody who can't print at home. So I got to write on regular sheet of paper. I don't want to ruin my ditto right here, but check out Old Man Berto. Old Man Berto wants a rectangular plot of farmland to grow some graphing calculators. Okay, now obviously the guy's out of his mind here. You can't grow graphing calculators, but he means well. In order to save money, Berto's plot will be bounded on one side by a river and on the other three sides by fencing, which is smart, right? Take advantage of a natural barrier right there, the river. Okay, so you only need fencing for three sides. And speaking of fencing, his measly teacher's salary has restricted his purchase of fencing to 800 meters. What is the largest possible area of the plot Old Man Berto can enclose? Okay, so this is a maximizing or minimizing problem. Some people are like, oh, which is it? Well, the largest possible area, largest means maximize, right? So we want to look at those keywords right there. And maximize what? Maximize area. Okay, so we obviously need to come up with an area function here. We got to get an equation for that thing. First you figure out what to maximize and minimize, then you get an equation for that thing. A lot of times it's geometric, like this one is right here. Pretty important, by the way, to know what's the largest possible area the plot can have if I'm restricted with this much fencing, okay? I want to make sure I have as much square meters as possible so that I could grow as many graphing calculators as possible. Obviously, nothing's going to grow, okay? But if it was corn or some kind of cash crop, something like that, obviously it'd be a little bit of a different story. I like to talk about the crazy old codger, Old Man Berto. So now maybe draw a diagram, okay? So we know we have a river right here. This could be where I live, a little van down by the river right there. And then we know it's a rectangular plot of farmland. All right, so it looks a little something like that. And we want to maximize area. We need an equation for area. So I'll say area is equal to, we don't know what the dimensions are of this rectangle yet. I'll call them X and Y for now. You can use any letters you want. Eventually we'll do these problems with the graphing calculator. You'll see that X and Y is a bad choice of variables because it can become very confusing when you're using the graphing calculator. But no graphing calculator today. Let's do calculus solutions. Obviously the area here would be X times Y. You could also call this distance X down here. Properties of rectangle. So look, find out what to maximize and minimize, get an equation for that thing, but now you need to get it down to one variable. And there's got to be some kind of restriction. They can't just be like, what's the largest possible area, the plot old man Berto can enclose? And you can be like, oh, the entire world, grabbing calculators everywhere. No, there's a restriction. There's only 800 meters of fencing. So x plus y plus x has to equal 800. It could equal less than 800, but that would not be a good way to actually maximize what your area is. Some people want to say the perimeter equals 800. Just be careful. We're not putting fencing right here on the river. Okay, so x plus y plus x is really 2x plus y equal to 800. And now you've created, using the restriction, a formula that relates x to y, so you can get rid of one of these variables. You could either solve for y or solve for x. It's easier to solve for y here because you don't have to worry about dividing by 2. You could just, you could solve for x if you want to. Without the calculator, try to make things as easy as possible. This is a relationship that will always be true at any particular time. Whatever x happens to be, y will be 800 minus 2x. And that's why you could say area is equal to, you could even say area of x right now is equal to, because we're going to take out that y, replace it with 800 minus 2x. And we can see the function is in terms of x only. So you could say a equals, you could still do that, that's fine. Or you could say a of x equals. Remember, this is like f, right? F of x, no difference. A of x, no difference. So I know a of x is equal to, get a little distribution going, 800x minus 2x squared. And I just got the formula down to one variable. Now you're supposed to get a domain, which always bothers people. But think about it. The domain, this is a function of x. The domain has to be in terms of x. And think about what you know about x. X is a distance. This distance right here, x has to be at least greater than 0, right? Technically, x could equal 0. But if it did, then y would equal 800. You just have, one vertical length right here. You wouldn't have a rectangle. The area would actually be 0. That's not a way to maximize area. That's a way to... Very good. Minimize area. Okay, so look, we're going to say that x has to be greater than 0. Weird way to write it, right? But that's because there's an upper element of the domain. There's something that x actually can't be bigger than. A lot of people want to say it's 800 because we only have 800 meters of fencing. But there are two x's. Okay, so if this x happened to be 800, this x would also be 800. And that's 1,600 meters of fencing. That's too much. That's why the maximum thing x could actually be is 400. And believe it or not, x could actually equal 400. You just have a distance of 400 here, a distance of 400 here, but you wouldn't have anything connecting them, okay? So once again, you wouldn't have a rectangle. That'd be a way to minimize area, not maximize area. Before the domain freaks you out, you could just put x greater than 0, and you would be fine, okay? You could still solve the problem. But really, the lower, element of the domain is normally just going to be 0. That represents when x equals 0. It's the smallest it could be. You could technically include the 0 in the 400 if you want, but once again, they're minimum, so it's kind of silly to include them here. The lower end, people never have a problem with. It's usually just 0. The upper element, remember, you don't want y to equal 0 either, okay? So if you actually set y equal to 0, remember what y is equal to? 800 minus 2x. So if you set y equal to 0, 800 minus 2x equal to 0. Solve this, you get 800 equals 2x, which means you get 400 equals x. So this 400 is really the x value that generates a y value of 0. Okay, that's how you get the upper element. Okay, just set the other letter equal to 0. We'll do it more and more. Once again, you could do these problems without having the perfect domain. The domain really starts to shine tomorrow when we use the graphing calculator, okay? So we'll talk about that more. Actually, it's not going to be tomorrow. I don't think that's going to happen until Monday, because I know that Thursday and Friday are holy days for many people. Wednesday, Passover begins at sundown. So Thursday and Friday, I think I'm just going to post like one problem with solutions to do, so it'll kind of be light days right there, and then we'll pick up, on Monday from that, the second day of this lesson. Sorry things are disjointed, but it is the way it is. Now look, we have a function. Function always represents... Very good. Y values, okay? It's just that the y values of this function, they represent areas, okay? And I want the maximum area. That means I want the maximum y value of the function that represents area. You got to be thinking of maximum. Well, surely there must be some sort of test. And there is the first derivative test. So if I take the derivative here, this is just like getting f prime of x. Looking for critical points, right? Critical x values. We get 800 minus 4x. You should check where it's non-existent, right? Critical x value where the derivative function is non-existent, but the derivative is always existent here. It's a linear, it's a polynomial. The original was polynomial, but you should see where it's equal to 0. right, if you solve this, add 4x to both sides. 4x equals 800, so divide by 4 on both sides. And what is that, 200? Let's get into units here. Remember the cardinal rule on units. If they give units, we give units. They gave units, it was meters. Just be careful. This right here is a critical x value, okay, where something important is happening on the graph of the area function. Is it a maximum? Is it a minimum? I don't know. I mean, that's where I draw a line. Not the f prime line, the a prime line, right? Because a is really an f spot. Tis it bounded? It is, okay, in this case from 0 to 400. You might not have that upper element of the domain. You might have an arrow over here. If so, you'll still be able to do the problem. Remember, put all critical x values on the a prime line in this case. And this is a place where if you graphed a, that area function, which we won't be graphing, you would see it has a derivative equal to 0 at x equals 200, has a slope equal to 0, horizontal tangent line. Remember, plug back into a prime. I'll plug in a 1 right here. 800 minus 4 times 1 is going to be positive. Plug in maybe, I don't know, 300 here. 800 minus 4 times 300, 800 minus 1200, which is negative. And you can see since a prime changes from positive to negative, the area function that this is describing the slope of will change from positive to, the area function will change from, increasing to decreasing, okay? And that's why there's a max right there. So now I know we have the max area when x equals 200 meters. Okay, and then you want to answer the question. You know, we did all this work. Think about it. This was just some fictional function f of x. We would have figured out that he had a maximum, a relative maximum at x equals 200. But that 200 really represents the amount of meters right here and here to give this thing the maximum area. And these problems are complicated. You know, eventually you do all this work and be like, wait, what the heck did I want? Oh yeah, what's the largest possible area of the plot that old man Berto can enclose? So you actually want area, and there's two ways to do it. We have two area formulas. You know, we have an area formula right here, and we have an area formula right here. This area formula is probably the easiest to use, but it's in terms of x and y, which means if x equals 200, you got to know what y equals. Remember, y is just 800 minus 2x. That's just going to be 800 minus 2 times 200, which is really 800 minus 400, which is 400 meters. So now I know that you have the max area when x is 200 meters, y is 400 meters. So that means that actual max area that they're looking for, it's actually looking for the y value of the absolute maximum right here, is going to be equal to x times y, right? So 200 times 400. 2 times 4 is 8, and then you can see we have 1, 2, 3, 4 zeros. So that's 80,000. This is meters times meters. That's why it's square meters, okay? Or just think about it as a measurement of area. Meters is not, a measurement of area. Square meters would be. You could also use this area formula right here. You wouldn't need y. It's in terms of x only. So you could actually do a of 200, because x was 200, which would give you 800 times 200 minus 2 times 200 squared. A little bit tougher to do without a calculator. That's why without a calculator, this is probably the one you want to go with. And that'll give you 8,000 square meters right there. Okay, so two different ways to do it. Make sure you answer the question. Maybe sometimes they just want to know the dimensions of the plot of maximum area. That would be these two answers right here, the 200 meters and the 400 meters. You could do this with the graphing calculator. You actually wouldn't use calculus. Second you get right here, you'd graph this function. His y values represent areas. You'd want to find the maximum area, graph this function, calculate the max. And you'll see it occurs at 200, 80,000. We'll do that in the next lesson, which officially won't be until Monday. Okay, so that's why these problems used to be extremely popular on the advanced placement exam, but they're very antiquated now. You don't see them like this. We do a lot of maximizing and minimizing next year, just not of real world situations, particularly like this one where you have to come up with the equation, because you could do them with the calculator so much quicker. But the main reason is that so many people were struggling with the algebra and actually setting these problems up. That's the hard thing. It's not the calculus that's usually difficult. Just to revise things, you could have included the 0 or the 400 here. You don't ever need to really include those endpoints. We'll do a problem or two next year where the extremas occur at the endpoints. You won't really see it this year. But if you did include that, you'll see at the 0, the area function starts and immediately increases. It's an endpoint min. Remember, if x is equal to 0, you only have 800, feet of fencing on Y, just one vertical line. You don't have a rectangle, okay, which means you'd have an area of 0. Here, the area function decreases, has a negative slope, then it stops. You could see another endpoint min. So you could either include those and then just, reject them, or you could just not even include them, okay? Use a little bit of common sense. Sometimes you're not maximizing, you're actually minimizing, okay? So let's actually, turn the sheet around, backing vocals, turn it round and round, and old man Berto is at it again, folks. That crazy old codger, what's he got himself into now? He is now building a much smaller rectangular plot of land to grow corn. Why corn, you ask? Well, corn, while less important than graphing calculators, is required for corny jokes. That's not funny. You heard about the parents who named their kid something and the kid ended up getting stepped all over. They said, why we name him Matt? Anyway, so he will use fence for all 4 sides of the plot this time. So no river. The plot must have an area of 100 square meters. That's a condition. I need that to be satisfied. What is the least amount of fence Berto can purchase to fence off his new plot? So apparently I'm growing corn, which is for corny jokes, which means obviously I'm still tripped out of my gourd, but corn is actually pretty good to grow and sell, so not really a problem there. That's, a nice coincidence. And I know it has to have an area of 100 square meters because I know how much corn I want to grow, but now I want to know what's the least amount of fence I can purchase to actually have that area of 100 square meters. So least is not maximize, least is minimize. Minimize. What am I minimizing? I'm minimizing the amount of fence. Minimize amount of fence. On God. Sorry, I don't know if you're into fencing. Some people say minimize perimeter. In this case, you're right. Okay, it is just the minimum perimeter of a rectangle, right? We got some rectangle here. I don't know what the dimensions are yet. I'll call them X and Y. Once again, when we start using the calculator, X and Y will bother you because you'll get X's and Y's in the calculator. I'll use B and H in a lot of those situations, but let's crawl before we can walk here. And look, we find out what to maximize and minimize, then get an equation for that thing, all right? I want an equation for the total length of fence, okay? And you can see that fencing is happening on all 4 sides of the plot. So that means the amount of fencing, which you could call F, you call it P if you want, because technically it is perimeter. F is kind of cool because then you end up with F of X, right? Just like the problems we did last topic. I'll use P just for the heck of it. And we know it's really X plus Y, which is really 2X plus 2Y. And the problem is this function right here, yeah, the Y values represent perimeters, but it's multivariable. I got to get it down to one variable. And they told me the area had to be 100 square meters. And I know if I do X times Y here, that gives me that area of 100. So now I could solve for X or I could solve for Y. I'll solve for Y just because we're used to doing stuff like that. Okay, Y is 100 over X. That's a relationship that's always true. So let's take out the Y here, replace it with 100 over X. And we end up with perimeters equal to what? 2X plus 200 over X. And that thing right there is an equation in one variable only. You could write it this way. You could write it this way. You can now say P of X if you want to is 2X plus, I'll write 200 over X is 200X to the negative 1. Can anybody guess why I'm doing that? Very good. I'm going to have to take a derivative eventually to find out the minimum Y value of this function right here. And I want to kind of avoid the quotient rule, use the power rule. But look, you should try to get a domain, which will always bother people, like I said. The domain here is going to be in terms of X, because this is P of X. If you solve for X over here, you would have P of Y. The domain would be in terms of Y. Think about what X can't be. X can't be 0. In the previous problem, X could be 0, right? But it was silly because that would just be a minimum area. Here, it's actually impossible for X to be 0 for 2 reasons. One, the algebraic reason. If X is 0, Y doesn't exist, okay? Why is that true? The conceptual reason? Well, our criteria here, our condition, is that the area of this plot must be 100 square meters. Area is a measure of surface. It's a measure of 2 dimensions. If you do not have a 2-dimensional object, you cannot get the area of that object. So if we decide to say that X equals 0 here, then there's only one dimension, right? You've wiped out this dimension right here. You just have these 2 lines Y, and that's not a 2-dimensional object, okay? So that means that X can't be equal to 0 because then you insisted this thing has an area of 100. It wouldn't have an area at all. It wouldn't even exist as a 2-dimensional object. I know that bothers you, some people anyway. You could just say X greater than 0, That's a domain that's pretty much always going to work. And here it's the proper domain. Some people say, oh, to get the upper element, set the other letter equal to 0. If you set y equal to 0, that means you get 0 equal to 100 over x. Cross multiply, 0 times x is 0. All right, 1 times 100 is going to be 100. This is an equation that's not true. So there is no upper element of the domain here. And that's because we forced it to actually be 2 dimensions. So you can't wipe out a dimension. Try not to worry so much about that. If you put x greater than or equal to 0, you'll be good to go. Now let's find out where this function has a minimum using the first derivative test. P prime of x equal to 2, negative 1 times 200, negative 200, x to the 1 less to the negative 2. Believe it or not, this thing is non-existent when x is equal to 0, but we already knew that. We couldn't include the 0 from before, so set it equal to 0. I'll just add this big fraction to both sides because it's negative right now. Don't let the algebra really bother you too much. 0 plus 200 over x squared is 200 over x squared equal to 2. And now you can cross multiply, draw the ire of Mr. Harrington. We'll bring it over here. 2 times x squared is 2x squared. 200 times 1 is 2 hundo. Divide by 2 on both sides. X squared equals 100. And then have that nice sigh of relief where you're like, oh, x is 10. Very nice when you take the square root of both sides. But wait, when you voluntarily take a square root, you got to take a positive square root and a negative square root. If you take the negative square root here, you get negative 10. Remember what x represents. He represents this distance, and a distance cannot be negative. So you can ignore that negative square root here. Just because, and this is 10 what meters? Just because this is a place where a derivative of the perimeter function is equal to 0 does not mean you have a max there. You could have a min there. So I need to figure out if it's a max or min. That's why I draw the line. The P prime line. My kids are screaming like crazy. Tis it bounded. Tis bounded only on one side, right? X greater than 0. So it's going to start at 0 and it's going to end when my wife stops nagging me, which is never. How about when my kids stop screaming, which is never? Put all critical x values on the P prime line. And that's where P prime equals 0. So if you actually graph this perimeter function, which we'll do on Monday, you'll see it has a slope of 0 at x equals 10. Let's see if it's a max or a min. Might not be a max or a min. Remember, it could be the increase in the increasing or the decrease in the decreasing situation. That won't happen here. Take a 1, plug it into P prime. 2 minus 200 over 1 squared is 2 minus 200, which is negative. If you plug in like a 20, 20 squared is 400. 200 over 400 is a half, and 2 minus a half is positive. And you could see the slope of P prime, changes from negative to positive, which means P is going to change from decreasing to increasing. And that's going to give us right there our, minimum perimeter that we're looking for. So we can say min perimeter, or how about min amount of fence, right? Because that's what they wanted. Min amount of fence. Got to write up this blurb here. You got to put a lot of steps, okay? Some people could just figure these things out in their head. I get it, but it's going to be a take-home test here. I'm going to want to show this work. We'll talk about it more on Monday, exactly what steps I need to see here. Some of them can be eliminated. Minimum amount of fence when, x is equal to 10 meters. And then go back. What the heck did they want? They actually wanted to know the least amount of fence. Okay, so you got to figure out what the least amount of fence is, which is really the minimum perimeter. 2 formulas for perimeter. You got this one, you got this one. This one's pretty sweet right here because x is equal to 10. So you can plug in 10 right now, right? And do P of 10 equal to 2 times 10 plus 200 divided by 10. Pretty easy to calculate. That's going to be 20 plus 20, which is 40. And then we're going to go meters there. Remember, we're doing meters plus meters, not meters times meters, okay? Perimeter is a linear measurement. It's not a surface, so it's not 2-dimensional, it's 1-dimensional. That's why it's m to the first, not m to the second. Remember, you could have also said min amount of fence when x equals 10 meters, then found what y is, right? So we know the relationship between y and x, okay? So 100 divided by 10 would be 10. So when x is 10 meters, y is 10 meters. Then if you did it that way, so really you already finished the problem, but if you did it this way, you could use this formula for the min amount of fence, okay, and get that your min amount, this, by the way, is the min amount. But another way to get that the min amount is equal to 40 meters is to write min amount here and use that second formula, right? 2x plus 2y, or 2 times 10 plus 2 times 10, which is still 20 plus 20, which is still 40 meters. Okay, so these problems right here, They're multi-step. I know they're not so easy. Really getting the domain bothers people more than anything else, but you can really do these problems without the domain. Remember, find out what it is you want to maximize or minimize, get an equation for that thing, get it down to one variable, and then try to get a domain, and then apply the first derivative test. Okay, you want to write up a little blurb that explains this line right here. Then you want to answer the question. But once again, we'll talk more and more about that as we do more problems. So try the homework tonight. I'm going to try to find some other problems, for you to work on Thursday and Friday. Just supplemental problems, probably one problem each day. So not really all that much going on there. But then Monday, we're going to hit the ground running. So that's another advanced placement calculus. That's the video I'm doing next. Pre-calculus honors, instructional video. If you have problems with anything, okay, let me know. Email me, send me a reminder. I hope everybody's doing well out there. Everybody's healthy and safe. Maybe I'll see you again before the school year ends. I guess we'll just have to see what we can see. Anyway, adios, y'all, and have a pleasant Easter. And we'll see you back here on Monday. See you later.